For this work, there are two main aspects. One is we take input from a single depth image, and the other is the fact that these images are actually from low-cost sensors, depth sensors. So for content-based shape retrieval is a long-existing problem, and it's very fundamental for a lot of applications. The standard interface, like you see here, either takes a sketch, human-drawn sketch, or a full CAD model as input, and these inputs are hard to get, and it's not very accurate to kind of characterize what you actually want to search. So when you think about, is there an easy to use interface? So it turns out we actually have it in the image search, where you just take a picture and you get similar images. So can we actually do something similar, like take a 3D camera and take a picture and I get a full 3D model? So actually we have. So thanks to the entertainment industry, we have very low-cost sensors like Kinect. And most recently, we even have these depth sensor on our mobile device, like mobile phone or tablets from Intel and Project Tango, Google Project Tango. So so now we have these sensors and data. The main challenge for this problem is we use only one single depth image as input. So you can imagine, like when you actually capture this query object, it can be captured from any kind of angle. So there's a large appearance variation due to the view angle. And also, because the database we use is a CAD model, which are designed by human, very accurate, very high quality, but the input is actually a sensor input, which is low quality. So there's a gap between this low quality input and the high quality database. So we have to address this issue. So here are our answers to these questions. So to represent the 3D model in the database, we use autoencoder, which have been shown to give very good results in modeling this manifold of input. So for us, we train one autoencoder specifically on each object model. So we render many depth images from different views for each model as input, and we reconstruct using the autoencoder. And then, as you can see here, this is kind of the weight, visualize the weight we get after training on one. This is a banana model. It actually captures all these shape features of this banana. And the different from the standard way using autoencoder, that they use the encoding output as feature to do some retrieval and matching, we actually don't use these intermediate output because we only care how similar this view to this model. So inspired by this ICML work, we directly compute a score which indicates how the likelihood of this view being generated from this object. So as an example, if we have a query of banana input to this banana model, we actually get a pretty high likelihood score. And for this kind of a ring query, we get lower score. And you can think of like the most straightforward way is you just take all these scores and do a ranking and get the final results. But as we mentioned before, there's this gap between input and output. So we did something different, like doing a domain adaptation to bridge this gap. So we formulate this problem as a classification. So we take this output score from these autoencoders, and we do a classifier to kind of fine-tune the scores. And to put them together, this is a whole architecture. And these are some results. So we directly jump into the results, and these are, so for the query we use UW RGBD dataset and the NYU depth dataset. And you can see from here, compared to other methods, our approach has much higher accuracy, precision in the low recall area, which means the top ranked results are pretty good. So these are some example retrieval results from different categories and different viewpoint. There are some failed examples because of the view. So thank you very much, and if you want to know more details, please come to the poster session.